You know what's unsettling about gravity? It doesn't do surprises. If an object falls inward, it speeds up. That's the rule every engineer, every navigator, every student learns first. So when Atlas started doing the opposite, it didn't look like a headline. It looked like a small line in a fresh trajectory fit. The kind you'd expect from a JPL grade pipeline. A tiny deficit in speed, right where the equations expect a gain. At first I thought it was the usual stuff. A bad timestamp, a calibration hiccup, a background star pulling the centroid, something boring that makes the anomaly vanish the moment you zoom in. But it didn't vanish. It came back. Not louder, not bigger, just stubborn. Like a metronome you only hear when the room goes quiet, tapping at the edge of the track. Navigation teams don't get paid to be dramatic. They get paid to make the future behave. Predict the next position, the next minute, the next week, and keep the error bars honest. That's why this is creepy in the specific way only tracking can be. Because the quiet break isn't a vibe. It's a residual, a repeated mismatch between model and motion. And here's the hook you should hold on to. It wasn't one odd data point. It wasn't one weird night. It showed up as a cycle, a pattern that returned when the geometry repeated. Picture it like this. Atlas swings through a familiar stretch of space, the gravitational slope should steepen, and instead the slope flattens by a hair, then it normalizes. Then later, it happens again. If you're thinking outgassing, you're thinking like a scientist. Comets vent. Jets act like tiny thrusters. They can push, they can twist, they can fake a maneuver without engines. But outgassing has a personality. It's messy. It changes with sunlight, spin, and cracks. It doesn't usually hit the same beat at the same phase, like a looped signal. Solar radiation pressure is another favorite culprit. Photons carry momentum. On small bodies, light can matter, but radiation pressure doesn't decide to slow you only in one repeating corridor. So the question becomes uncomfortable fast. What kind of force looks like a brake, shows up where gravity should accelerate you, and repeats on a cycle tied to geometry? And no, I'm not saying it must be propulsion. I'm saying the numbers behave like something is subtracting velocity in a directed way, small but consistent enough to leave a fingerprint. This is where people lose the thread, because it sounds technical, but it's actually simple. Prediction says, you should be here. Observation says, you're a little behind. Not by miles, not by days, by an amount so small you'd ignore it, unless it kept happening at the same points like a scar that reopens on schedule. That's when the story flips from random weirdness to structured weirdness. Random is easy. Structured is the thing you have to explain, because structure implies a mechanism. Now everyone online is staring at the loud stuff, tails, brightness, big claims. Meanwhile, the quietest clue is hidden in the boring product, trajectory updates. Because an orbit isn't just a line on a graphic, it's a negotiation between forces. Gravity, sunlight, gas flow, measurement noise. If one of them cheats, the negotiation shows it. The cycle matters most. If the braking effect lines up with a repeating orientation, it hints at something that turns with the object, or something the object passes through again and again. A spin-related jet could do that, in theory. If vents fire when a particular face rotates into the right thermal condition, you can get periodic pushes that look clean. But then you'd expect brightness changes, you'd expect a link between activity and thrust, you'd expect messy variations as the surface evolves. The quiet break is too tidy. So let me ask you the question nobody likes to say out loud. If Atlas can lose speed on cue, even a little, what else can it modulate without looking like it's doing anything? And if it's not cue, if it's environment, then what is the environment? A thin dust sheet? A plasma structure? A magnetic interaction we usually ignore because nothing this odd crosses it. Here's why serious trackers would lean in even if nobody posts a statement. Residuals are how you catch the real world lying to your model 1 millimeter at a time. Once you see a residual repeat, you can't unsee it. You start looking for the period, the phase, the trigger. You try to break it with alternate assumptions, and you watch it survive. And that's where we are in this story. Not at answer, but at pattern. A quiet, repeating drag that shows up like a heartbeat in the math. Now that you know that, you probably want the timeline. When does it happen again? When does Atlas hit the next repeat of that geometry and show the same deficit? The uneasy part is that cycles imply predictability, and predictability is the one thing a random comet shouldn't give you for free. So stay close, because the next pass is where the simple explanations either finally win, or they fail again, and the quiet break becomes the first real clue that Atlas isn't flying like a normal visitor. So the next thing you do is you stop arguing online and you start watching like a tracker. You ask one boring question that changes everything. When does the geometry repeat, and what does the residual do then? Because if it's a fluke, it won't come back on time. It'll smear out. It'll flip sign. It'll dissolve into noise the moment the dataset grows. But if it's real, you get a gift and a curse at the same time. A gift because a repeating anomaly can be predicted. A curse because now you have to explain a mechanism that can keep a schedule. The teams at NASA Jet Propulsion Laboratory don't believe in anything. They test models. They swap force terms in and out. They rerun the fit until the universe either cooperates or refuses. And one of the first swaps is always the same. You let non-gravitational forces breathe. You give the comet permission to be messy. Tiny jets, asymmetric outflow, a push that depends on how the surface warms. If the quiet break is outgassing, the math can usually swallow it. You'll see a better fit, smaller residuals, and the acceleration term will point roughly away from the sun, like a normal comet trying to vent. But what if the term points the wrong way? Not away, not random, but aligned like a deliberate counterthrust, repeating at the same phase like it knows when to fire. Now you're in the uncomfortable zone where the model can be made to fit, but only by giving the object a behavior you don't like. A jet that turns on in the dark. A vent that prefers braking over pushing. So you do what you always do when the story starts to feel too neat. You look for collateral evidence. If gas is pushing, the coma should change. The brightness should wobble. The spectrum should show a little more CO, CO2, dust, something. And if you see none of that, the jet explanation starts to feel like a patch, not an answer. Like putting tape over a crack because you don't want to hear the house settling. Here's the detail most people miss. A braking signal is easier to hide than an accelerating one. Accelerating tends to flare activity, brighten tails, make pretty images. Braking can look like nothing at all if it's subtle and steady. That's why it sits in the tracking products, not the photos. You won't notice it in a thumbnail. You notice it in a plot where prediction and reality stop agreeing. So the next cycle becomes a test. Not a cinematic event, just a window on a calendar where the geometry repeats and everyone quietly checks whether the same deficit returns. If it returns, the simplest interpretation is still natural, a rotating nucleus with a vent that only opens when a specific face warms, and that face happens to be oriented, so the push acts like a break from our frame. But even that simple explanation has teeth, because a vent that repeats cleanly implies stability. It implies the surface hasn't changed much. No new cracks, no clogged nozzle, no chaotic seasonal behavior. And comets are not famous for stability, they're famous for tantrums. They spin up, they shed, they fracture, they change their own rules as they get closer to heat. So you start watching for spin. Light curves, subtle periodic flickers, anything that gives you a rotation period, because if the brake is tied to rotation, it should lock to that rhythm. If it's tied to environment instead, rotation won't help you. The timing will follow space, not the body. It will line up with where Atlas is, not how it's facing. That's when people whisper about drag. Not atmospheric drag, obviously, but something thin, something you'd normally ignore because interplanetary space is supposed to be too empty to matter. A dust sheet, a plasma ribbon, a structured solar wind feature that behaves like a gentle hand on a fast object, taking a microscopic fee every time it passes through the same corridor. If that sounds far-fetched, remember this. We already accept that space has weather. The solar wind isn't uniform. Magnetic fields fold and reconnect. Streams and shocks exist. The problem is scale. Those effects usually show up in charged particles and spacecraft telemetry, not in the bulk motion of a rocky ice nucleus on a hyperbolic path. So if you want to test environment, you look sideways. You ask if anything else moved oddly at the same time. A probe, a known asteroid, a satellite, feeling a tiny extra tug. And that's where the story gets tense, because it's hard to do. Space is full of little perturbations, and nobody writes press releases about a millimeter per second. But a repeating break gives you leverage. You can stack passes. You can compare epochs. You can separate random noise from a pattern that keeps showing up in the same place like a watermark. And the day you see the watermark, you stop thinking in terms of one anomaly. You start thinking in terms of a layer of the system we don't map well. Now you might be expecting me to jump to the wild conclusion, the one that turns a comet into a machine. I'm not doing that. Not because it's boring, but because the boring explanations still haven't been exhausted. However, I will tell you what makes engineers uneasy. Control doesn't have to be loud. Control can be tiny, repeated, and timed. If you can shave speed at the right points, you can reshape a path over months. And if you're a natural object, you don't decide to do that, you just respond to physics. So the whole game is figuring out which physics can mimic something that looks like choice. The next step is to look closer, not wider. Infrared to see if one hemisphere is warmer than it should be. Radio to see if molecules spike in sync with the break. High cadence astrometry to catch the drift as it happens. Because the most dangerous mistake isn't believing the spooky version. It's dismissing the anomaly so fast you never build the test that could kill it. So we follow the calendar. We wait for the geometry to repeat. And when it does, we don't ask, is this scary? We ask one cleaner question, did the universe do the same wrong thing again? If yes, then Atlas is teaching us something. Either about how comets can behave when they're rich in volatiles we rarely measure, or about a corridor of space that steals momentum in a way our models don't include. And if no, If the break vanishes, then we learned something too. We learned how easy it is for a few clean data points to hypnotize the brain into seeing a pattern. But here's why you should stay close. Patterns don't usually vanish quietly. They either die in daylight or they come back sharper the moment you stop looking away. And the next update, the next fit, the next cycle is the moment where a quiet break turns into either a footnote or the first chapter of a much larger problem. So the team does what teams always do when the sky stops behaving. They tighten the model until it squeaks, then they loosen it on purpose to see what falls out. They split the tracking in practical ways. They compare speed from radio shift against distance from timing, and they check whether different stations tell the same story. If the break is real, it should survive the swap. If it's a processing ghost, it should die the moment the pipeline changes its shoes. And the eerie part is that it survives just enough to stay interesting. The curve doesn't collapse, it just refuses to become perfectly normal. Now let me make this simple. Tracking is basically a conversation. We send a tone, the object answers with a slightly shifted tone, and that shift tells us speed. When the shift says a little slower than predicted, that's not a vibe. That's physics arguing with math, one tiny syllable at a time. So they draw a clean line in time. Here's where gravity should steepen the slope. Here's where the slope goes soft. That softness is the quiet break. The cycle shows up when the geometry repeats. Not the same date on a calendar, but the same relationship between the object, the sun, and our line of sight. That matters because it narrows the suspects. A random jet is sloppy. A geometry-tied effect is picky. Picky things usually have a reason. The next move is to check the light. If thrust is hiding in outgassing, the brightness should twitch and sink. If brightness is flat, thrust starts to feel like a stretch. But comets can be sneaky. Gas can be thin and still push. Dust can be absent, and a jet can still act like a tiny engine, especially if it vents mostly invisible molecules. So you watch the spectrum, not like a fan, like a forensic tech. You look for a bump that returns on the same beat as the break. And then you notice a second oddity. The break doesn't scale the way sunlight scales. It doesn't simply grow as the object gets warmer, like you'd expect from normal activity. Sometimes it's stronger when it should be weaker. Sometimes it fades when it should flare. That's a dangerous sentence, because it hints at a trigger we haven't named. I'm not giving you a simple villain. I'm giving you a problem, a trigger that isn't just more sun equals more gas. One natural trigger is rotation, but rotation alone is not enough. Rotation gives you a rhythm, sure, but the cycle we're seeing is tied to space, not just to spin. So the team overlays the events, same corridor, same phase, same deficit. It starts to look like the object is passing through a thin region that steals momentum. If you hear drag, your brain wants air. Forget air. Think of a sparse cloud, dust and plasma so thin you laugh at it until you remember the distances and the time. A tiny force applied gently for long enough can do real work. It can bend a path without a dramatic shove. It can make a visitor arrive late by minutes, then hours, then days. And if that force is localized, it can repeat. You cross the same invisible seam and you pay the same invisible toll. So where would such a seam come from? One answer is solar wind structure. The sun throws out streams and folds its field, and sometimes those folds are long-lived. Another answer is debris, a leftover sheet from an old comet, a trail that never fully dispersed, a ribbon of grains, sharing an orbit like a silent road. If the visitor is cutting across that road, it could feel a drag that looks like a break, not because the road is thick, but because it is there at all. Here's the catch. If there is a road, it should leave traces, tiny impacts, brief flashes, a change in the glow around the nucleus, something we can see, even faintly. So the watchers widen their net. They look for microflares, for any softening in the shape of the light blob, for any hint the object is plowing through something. Most nights nothing obvious happens, and that is what keeps the tension alive, because absence of proof does not kill a tiny force. It only means the force is subtle, or the evidence is hiding in channels we do not watch often enough. Now we hit the timeline question. When does the next repeat occur? When does the corridor line up again, and what should we see if the break returns? If the break returns, you get a prediction, a narrow window where the error should dip, where the object should run a little behind the model like it did before. And prediction is a trap, because if you can predict it, you can test it, and if you can test it, you can stop guessing. So the next pass becomes the cleanest scene in the whole story. Not a photo, not a tale, just a set of dots on a graph and a question that can finally be answered. Does the deficit appear again at the same phase? Does it match the earlier size? Does it drift forward or backward in time? If it drifts, that points to environment. If it locks, that points to the body. Either way, you learn which direction the truth is leaning. This is where the calm voice becomes almost too calm, because the moment you narrow it to two mechanisms, you also feel a third one in the shadows. A mechanism that can sense geometry and respond. A mechanism that can turn a tiny push on and off when the map says now. You don't need science fiction to feel the chill. You only need to imagine navigation that is not fully passive. So the team does the responsible thing. They build the mundane tests first, better positions, better cadence, cross-checks with independent telescopes. They also do something that sounds small but matters. They reprocess the past, hunting for the same pattern earlier than anyone thought to look. Because if the cycle was there before, it will be there again. And if it was not there before, then something changed, and that is the scarier result. And in the quiet of that reprocessing, another question crawls onto the table. What if the break is not breaking at all? What if we are seeing a shift in how the object presents itself? A changing center of the glow that makes it look like it moved less than it did. That sounds like a trick, but it is real. When a body is fuzzy, you track the center of its light, not a hard surface. If the glow leans, the center leans too. So suddenly the quiet break could be a quiet illusion, a halo that slides like a veil, shifting the measured position without shifting the real path. But the illusion would still have to repeat. It would still have to lock to geometry. The story doesn't get easier, it only changes costumes. Either way, the next cycle is the judge, because an illusion tied to viewing angle will leave a different signature than a force tied to motion. So we arrive at the same cliff again. A predicted window, a silent graph, a corridor in space that may or may not exist. And if you want the honest reason this keeps people awake, it's not fear of impact, it's fear of being wrong in a way that matters. Because if a tiny visitor can carry a tiny anomaly and we miss it, then the outer system isn't quiet. It's just quiet in the channels we got used to watching. That's why this story isn't about one object. It's about whether our models are missing a whole class of subtle effects. And if they are, then Atlas isn't a monster. It's a warning label, the kind you only notice after something already slipped through. And this is the moment the story stops being about, is it weird, and becomes, can we isolate it? Because once you can isolate it, you can measure it. And once you can measure it, you either kill the anomaly or you promote it. So the clean test is simple to say and hard to do. You predict the next window, you track Atlas through it with higher cadence, and you watch whether the residual dips again in the same direction. If it dips, you don't celebrate, you get suspicious, because repeating means the universe is giving you a handle, and handles usually belong to real mechanisms, not to random noise. If it doesn't dip, you also don't celebrate, you ask what changed. Different instruments, different phase angle, different data weighting. A pattern that vanishes can mean it was fake, or it can mean it moved. That's why the team starts stacking independent eyes, optical astrometry from different observatories, different pipelines, different reductions. You wanted the same quiet break to show up even when the math is done by strangers. Because if the effect only exists in one reduction chain, it's likely a software ghost, and the scarier part is that software ghosts can look perfectly periodic if the geometry triggers the same bias every time. So they reframe it as two competing stories. Either Atlas is actually losing speed, or our measurement of its center is sliding in a way that impersonates a loss of speed. That center problem sounds boring, but it's vicious. A comet is not a hard dot, it's a fuzzy glow. If the glow shifts as the viewing angle changes, the center you track can drift without the nucleus moving. And if that drift repeats with geometry, you get exactly what we're seeing. A cycle, a deficit, a quiet break that is really a quiet miscentering. So the next step is to look for shape changes, not just position. Does the coma lean? Does the tail brighten on one side? Does the light distribution skew right when the residual appears? If the residual is a force, you might see nothing in shape at all. A tiny push can be invisible, but if it's a centroid illusion, the shape should betray it, even slightly, like a shadow leaning. That's where timing becomes everything. You don't just need more data. You need data at the exact phase where the effect is predicted. Otherwise, you're just collecting pretty points that never touch the question. And while that's happening, everyone else keeps doing what people do. They chase the loud narrative. They argue about what Atlas is. They miss the one place where the object speaks without a voice. Because tracking is the object talking. It can't fake a Doppler shift with vibes. It can only fake it by changing physics, or changing how we measure physics. So we zoom out for a second. Suppose it's real drag, real momentum loss, real braking. Then Atlas is passing through something. A thin region, a corridor, a toll gate made of dust or plasma. If that corridor exists, it should not be unique to Atlas. Other small bodies might feel it too. Just not enough for anyone to notice unless they're looking for millimeters. And that opens the wider question. How many corridors like that do we not map? Because most objects never cross them in a measurable way. Or we never track them with this level of obsession. Now suppose it's outgassing, a jet that acts like a brake at specific orientations. That would mean the nucleus has a stable vent pattern, like a pinhole that opens only when conditions align. But stable vents over repeated cycles imply a surface that isn't changing much. That is unusual for an active body, especially as it heats. So if outgassing is the answer, Atlas is unusually disciplined. And if it's neither drag nor outgassing, then you land on the third bucket, a systematic bias tied to geometry. the kind that lives in the relationship between telescope, background stars, and a faint fuzzy target. That bucket is the least cinematic and the most common. It's also the one that can fool smart people because it doesn't look like an error. It looks like a clean, repeating fact. So the real tension here isn't what is Atlas. It's whether the cycle survives the brutal things scientists do to fragile ideas, independent replication with different tools. Because if two separate teams, using separate reductions, see the same dip at the same phase, then you can stop calling it a pipeline problem. You have to treat it like a physical signature. And then the story turns darker, not because it becomes alien, but because it becomes structural. A structural effect means it's part of the environment or part of the body, and either way, it can happen again. That's why the next update matters more than any image. The next window is the trial. Either the quiet break returns on schedule, or it breaks its own pattern and forces a new explanation. So keep your eye on the boring deliverable, not the headline, the residual plot, the place where prediction and reality either reconcile or refuse to shake hands again. So here's what happens next. Nobody declares anything. They just tighten the watch. More points, closer together, fewer gaps where the anomaly can hide and pretend it never existed. And the weirdest part is how quiet the room gets when the window approaches. Because you're not hunting fireworks. You're hunting a tiny dip that only matters if it repeats in the same place. You can feel the difference between a story and a test. A story wants drama. A test wants timing. A test wants the same geometry again, so the universe has no excuse. When the window opens, the tracking doesn't look like a chase. It looks like patience. Dot after dot, night after night, until the curve either behaves or refuses again. If the residual drops right on cue, the brain does a dangerous thing. It starts expecting it. And expectation is exactly how you get fooled by a pattern that isn't real. So the only sane response is cruelty. You try to break the pattern on purpose. You change the weighting, swap catalogs, recenter the astrometry, run the fit like you're trying to disprove yourself. And if the dip survives that abuse, you don't call it proof. You call it stubborn. Stubborn is the word engineers use when the universe keeps contradicting their cleanest model. Now you might ask the simplest question. How big is the break? Is it dramatic? Is it enough to change anything meaningful? Or is it just a rounding error dressed up as a mystery? Here's the honest answer. Even a rounding error matters if it repeats. A tiny effect applied in the right phases can move an arrival time, reshape an arc, and shift where next actually is. That's why people care about millimeters per second. Not because it's flashy, but because millimeters per second, repeated, can become the difference between predictable and unknown. And this is where the quiet break becomes a personality test for the object. Does it scale smoothly as it approaches the sun, like normal activity would, or does it keep the same strange rhythm? If it scales with heat, then fine. You're probably looking at venting, ugly, natural, hard to model, but familiar. The comet is leaking, and the leak sometimes points the wrong way. But if it does not scale with heat, you start looking for geometry triggers. Viewing angle, phase angle, line of sight effects that move the measured center without moving the nucleus. That centroid trick is the cleanest liar in astronomy. If the coma brightens on one side, the center slides. The object looks late, not because it slowed, but because we tracked the wrong middle. So the next question becomes visual, not numeric. Does the coma tilt when the break appears? Does the shape skew? Does the brightness lean like a flashlight beam across fog? Most people think that's too subtle to matter. They forget we're not eyeballing a picture. We're measuring tiny shifts over long baselines, where subtle becomes decisive. And if the shape does not change, you circle back to force. A real force can be invisible. A thin push can leave no tail clue, especially if the gas is mostly transparent at the wavelengths we love. That's when the spectrometers get pulled into the room. If molecules spike in sync with the break, you have a story. If they don't, you're left with silence and a residual that won't confess. Now there's another layer people hate to talk about, timing bias. When you combine data from different nights, different stations, different weather, you can accidentally create a rhythm. So they do something ruthless. They isolate single station segments. They ask whether one side alone sees the dip or whether the dip exists even when the network is split. If it exists everywhere, it's harder to call it bias. If it lives in one chain, then it's probably a shadow cast by the method, not by the object. But here's the thing that keeps the tension alive. The dip isn't big enough to be obvious. It sits right in the zone where real physics and real mistakes look identical. That's why the debate doesn't explode. It simmers. You don't scream about a millimeter. You stare at it until it either turns into a centimeter or disappears. And while that staring happens, a wider thought starts creeping in. If this is environmental, if space has a thin corridor that steals momentum, then Atlas is not the main character. The corridor is the main character. Atlas just happens to be the one crossing it on a path we can track cleanly enough to notice the toll. So you start wondering what else crossed it without anyone noticing. A small comet with sloppy data. A rock with sparse observations, a spacecraft with a different tracking regime. This is how you end up with the most unsettling sentence in the room. What if we've seen this before and called it noise? Because noise is a graveyard. You can bury any anomaly there and sleep fine. Until one day the same anomaly returns with a cleaner signature and you realize you buried a mechanism. Now that you're thinking that way, the story widens fast. Not into fantasy, into inventory. How many subtle effects are missing from our standard model of small body motion? We model gravity, we model sunlight pressure, we patch in non-grav terms for comets, but we do not map every thin structure in the heliosphere like it's a road system. And if Atlas keeps paying a toll on a schedule, that suggests the roads are real. Not roads you can see, roads you infer because the math keeps bruising the same way. At this point you're probably waiting for a verdict. I'm not giving you one, because the only honest verdict is that the next cycles decide everything. Each repeat is a vote for force, a vote for illusion, a vote for bias, and the more votes you collect, the harder it becomes to dismiss the pattern as coincidence. So the countdown isn't to impact, it's to the next geometry. The next time prediction and reality meet in the same corridor and either reconcile or disagree again in the exact same accent. And if they disagree again, stay with me, because then the quiet break stops being a curiosity and a fit. It becomes a feature of the object's story, and features always lead to the next question. If Atlas can look like it's breaking on a schedule, what else can it do on a schedule that we haven't thought to measure yet? Now you're probably wondering what the next cycle looks like in practice. Is it daily, weekly, monthly? The uncomfortable answer is that it depends on geometry, not on a human calendar. In the tracking notes, it doesn't read like every Tuesday. It reads like when this angle returns. When the sun, the observer, and Atlas line up in a familiar way, the same soft dip tries to appear. That's why the window feels eerie. You can mark it ahead of time. Not because Atlas promised anything, but because the sky repeats its own arrangements like a machine turning a wheel. So when the next window approaches, everyone stops debating what it means and focuses on one brutal test. Can we catch the dip forming in real time instead of noticing it later in a cleaned up fit? Real-time tracking is a different kind of pressure. You can't hide behind averages. You see the residual breathe point by point and you feel the moment it either stays flat or starts slipping behind. If it slips behind again, you immediately ask the most boring question with the sharpest teeth. Does the line of sight change explain it? If yes, it's likely a measurement illusion. If no, it's pushing toward physics. Because illusions love viewing angles, a coma that leans, a tail that brightens on one side, a glow that shifts the centroid. Those effects are geometry sensitive and repeatable, and they don't require any real force. But forces have tells too. A real force will correlate with a direction in space. It will leave a signature that stays even when you change star catalogs, reducers, and assumptions about how the light is distributed. That's why the next pass isn't just more data, it's different kinds of data. High cadence astrometry to catch the drift, and spectroscopy to see if the chemistry twitches when the break shows up. And here's where the story tightens. The break doesn't need to be big, it only needs to be consistent. A small subtraction, repeated at the right phases, can reshape the long arc without ever looking dramatic. That's the part people underestimate. They think control has to look like a burn, but orbital history is written in whispers. If you whisper the same thing often enough, the future changes. Now imagine the cleanest natural explanation that still fits the cycle. A stable vent, not a chaotic outburst, but a stubborn little nozzle that fires when a particular face hits a particular condition. That condition could be sunlight, but it could also be shadow. Thermal stress can open and close cracks. A seam can breathe like a valve, and the push can look designed, even when it's just geology. But that explanation comes with a price. If the vent is stable, Atlas is stable. And comets are usually not stable for long once they start waking up. They evolve, they shed, they change their own surfaces. So if the break keeps repeating cleanly over multiple cycles, the natural vent story starts feeling less comfortable. Not impossible, just increasingly specific. Like the universe is forcing you into a narrow corridor of explanations. Which brings us back to the other corridor. Not a vent corridor, a space corridor. A region the object crosses where something thin and persistent steals momentum like a toll you can't see. If that exists, it raises an immediate quiet alarm. Because the heliosphere is not empty. It has structure. It has sheets and folds and streams. And we don't map them like roads. Most of the time we don't need to. Most objects are tracked too loosely for a millimeter per second toll to matter. But Atlas is being watched like a hawk, and that makes the invisible suddenly visible. So the question expands. If Atlas is paying a toll, how many other bodies have paid the same toll and we called it noise? How many subtle drifts have been buried because no one had a reason to obsess? This is where you feel the shift from one weird comet to a missing layer in our model. The scary part isn't Atlas itself. The scary part is the possibility that the system has features we don't account for. And then there's the third option that nobody likes because it's mundane and humiliating. A systematic bias that repeats because our methods repeat. A pipeline scar that shows up every time geometry triggers the same weakness. That's why independent replication matters more than any narrative. Different telescopes, different teams, different reductions, and the same dip at the same phase. If that happens, the ghost story dies. Or doesn't die, and if it doesn't, the quiet break becomes something you have to carry forward, not as a conclusion, but as a constraint. Any future explanation has to respect that repeating fingerprint. Now let's talk about what can go wrong, even without impacts and Hollywood endings. A small, persistent anomaly means uncertainty grows, prediction degrades, and if prediction degrades, planning gets harder. Because the moment you can't forecast a path cleanly, you can't confidently say what it will pass near, what it will graze, or what gravitational knots might amplify tiny errors into bigger changes. And that's the next hook. If the break is real, it is not just slowing Atlas, it is steering the uncertainty. It is deciding which future questions become urgent and which ones stay theoretical. So we watch the next cycle like a court date. Not to prove a fantasy, but to narrow reality. Either the dip returns again and the pattern hardens, or it breaks, and we learn what we mistook for structure. But if it returns, stay with me. Because then the obvious question stops being, why is it slowing? The obvious question becomes, what else is it doing that we haven't learned to measure yet? Because once you start predicting the dip, you start hunting for it like a heartbeat. You don't ask, is it spooky? You ask, can we measure the beat without touching it? The navigation team builds a blind test. They lock the model before the window, then they refuse to tweak it midstream. If the curve still sags, the sag belongs to the sky, not to their hands. And they do the cruelest thing. They ask a second group to process the same nights without telling them what to look for. No hints, no target, just raw positions and timestamps. If both groups see the same soft delay at the same phase, the easy excuses get thinner. Not gone, but thinner, like fog when the first sun hits it. Then the question shifts from what is it to where is it? Is the dip tied to a location in space, like a thin seam the object crosses, or tied to the object's own body, like a valve turning on? To separate those, you watch the phase drift. If the dip slowly slides along the timeline as the orbit evolves, that smells like environment. If it stays locked to the same attitude, that smells like rotation. So you try to learn the spin, and you do it the boring way. You stare at faint brightness wiggles and hope the object is honest enough to repeat its own flicker. If a clear rotation period pops out, you overlay it on the breaking windows. When the two rhythms line up, you breathe. When they refuse to line up, you go quiet. Because a mismatch means the cycle is not a simple, hot-face vents gas story. It means something else is setting the schedule, something that doesn't live on the surface. That's when people start paying attention to the space around it, not the rock itself. Solar wind speed, magnetic folds, dust trails, anything that could form a corridor with a memory. And no, space shouldn't have memory the way a road does, but it can have structure that lasts longer than you think, especially when the sun keeps pumping the same patterns outward. If Atlas keeps losing the same tiny slice of speed in the same slice of space, that slice becomes a map feature. Not visible, not photographed, but real enough to tax motion. Now imagine you're wrong, and it's just a centroid trick, a coma that leans, a glow that shifts, and our center slides behind the nucleus by a fraction of a pixel. That would still be a story, because it would mean Atlas can change its apparent position without changing its path. In tracking terms, that's a mask you can't ignore. So they look for asymmetry, not with poetry, with math. Does the light blob skew right when the residual drops, and does it skew the same way on every repeat? If yes, the quiet break turns into quiet bias, and the mystery becomes optical. Still unsettling, but grounded. You can attack optics with better images. If no, you're back to forces, and forces are harder. A force doesn't care about how pretty your picture is. It only cares about momentum and direction. At that point, the team starts writing the only sentence that matters. If the effect persists, the ephemeris uncertainty grows. Translation, we will know less tomorrow than we do today. And that's the real risk here. Not impact, not apocalypse, but a widening cone of maybe, where future close passes and gravitational nudges become harder to forecast cleanly. Because small bodies don't travel alone. They pass through fields, they pass near planets, they pass near each other. Tiny errors today can pick a different fork months from now. This is where the story gets bigger without getting louder. A repeated millimeter per second toll could reshape which planet gets the next close look, which resonance gets tickled, which path gets chosen. Now you probably want the one thing everyone wants, a reason, a mechanism that sounds simple enough to repeat and strong enough to believe. The clean natural mechanism is still outgassing. Invisible gas, low dust, a vent that fires like a whisper. It can push against motion and look like braking. But if it's outgassing, you expect a companion clue. A faint chemical pulse, a subtle brightening, a change in the halo, something that follows the same rhythm. So they schedule deeper spectral looks right on the window. Not when it's convenient, but when the anomaly is supposed to happen. Because timing is the knife here. If the chemistry spikes, you gain a handle. If it doesn't, the vent story gets cornered and the corridor story grows teeth. The corridor story has its own test. If space is stealing momentum, then the effects should care about velocity through the region, not just about sunlight on the nucleus. That means the dip should scale with how fast Atlas cuts across the seam. Faster crossing, sharper signature, slower crossing, softer one. So you watch the shape of the dip, not just its depth. Is it a smooth sag over days, or a sharp kink over hours, like crossing a boundary? And while the graphs build, the human brain does the thing it always does. It starts treating a repeating pattern as intention, because intention is the simplest story we know. That's why the best people in the room keep repeating the same warning. Pattern is not purpose. A clock can be a rock, a rhythm can be weather. But then the pattern keeps showing up and the warning starts to sound like prayer. Because every repeat is another chance for the anomaly to die, and it refuses. So the question changes again. If it's real, why is it so quiet? Why doesn't it announce itself with obvious flares, obvious jets, obvious images that anyone can point to? And the answer is that the quietest forces are the ones that survive. Loud forces burn themselves out. Quiet forces can act for months and never draw the eye. Which means the next chapter isn't about a big reveal, it's about accumulation. Cycle after cycle, the quiet break either fades into noise or hardens into a law we didn't write down. And if it hardens, then Atlas becomes more than a visitor. It becomes a calibration target, the object that taught us where our model ends and the system starts. That's why the next window matters more than any rumor, because the window doesn't care what you believe. It only cares whether prediction and reality disagree again, on schedule.